reinforcement in tension, more steel reinforcement in tension and less steel reinforcement in compression. So this is the reason why called double reinforced section. Actually, we have two situations or two options, not option, two situations. First one may be your compression steel yields. So stress in this steel reinforcement equal F yield. We will start with this option. We will assume compression steel yields and start your calculation. Then we need to check if your steel yields or not by calculating what is the strain in this steel reinforcement. Epsilon steel prime. Do you remember how can we get this value?
Similar triangle.
Triangle similarity between this little triangle and the biggest one. If your strain value equal or greater than yielding strain, which equal F yield divided E steel, it's okay. Your calculation is done. You are done. Your moment of resistance is done. But if not, your strain less than epsilon yield, we need to do more calculations because we have on the second situation. So your stress in steel reinforcement in compression does not yield. So we will assume it Fs before yielding. To calculate your Fs equal epsilon steel prime times E steel. Epsilon steel prime from triangle similarity equals this value times E steel. Put this value instead of F steel. So the only unknown in your equilibrium equation is your distance C. After you removed A and put it by beta 1 C. You will get equation from second order, quadratic equation. You solve for C and then you can get your moment by assuming your cross section equal. First part, your concrete with sum of area steel 1. Then the remaining of steel with compression steel. So we have area steel prime with area steel 2 is the second part. Remember, this part plus this part equal the whole cross section. So area steel 1 plus area steel 2 equal area steel. Your steel reinforcement here plus area steel bar equal your area steel bar. And put it in your mind, your area steel bar equal area steel 2. This part has a tension force, with this part has a compressive force, the distance in between D minus A divided 2. This part can give you Mn1. We have a tensile force here, compressive force here, the distance in between D minus D bar. This bar can give you Mn2. So your final moment of resistance, nominal moment of resistance, Mn1 plus Mn2, then you can add your factor of safety phi equal 0.9 to get your design moment. We covered all of this stuff last week. Today, we will talk about something different. What we learned before, just only 4 rectangular beam. Only single beam like this, between this support and this support for bridge, whatever. If you are trying to get cross section in this beam, your cross section looks like rectangular or rectangle cross section. But most of the time we have concrete slab, concrete deck. So your beam with the concrete slab, if you make cross section, you can expect something different. which called T section. T section. Reinforced concrete floor or slab system are placed with supporting beams. The slab can function as a flange for the beam. The portion of the beam below the slab is called web. This part called web. And this part called flange. And the total cross section called T section. So if we have concrete slab with beam, both of them together called T section, not rectangular section. So we need to understand how can we design T sections. First of all, how much from your slab is working with your stem or web? In a different meaning, your flange of the cross section has a width called B flange, effective flange width. Not the whole slab is working with your beam. No, just a little bit of the slab. This a little bit of width called effective flange width. According to ACI, we have 3 different values for this be effective. Quarter span, 16 T slab plus B web, or be actual center to center. I'm sorry, I cannot understand anything. Okay, your beam supported between 2 columns, and this beam has a span equal L. If you divide this L by 4, you can get a value for B flange or B effective. Your slab has a thickness called HF, and your beam has a width B web. If you multiply 16 times slab thickness plus B web, you will get another value for B flange. This beam and this beam and this beam, each beam has a distance between the adjacent beam from center line to center line. So we have another distance, B flange. So this one, B actual, center line to center line. Your beam is repeated. So this beam can support from this center line between this beam and this beam, and from this center line between this beam and this beam. So we have 3 different values of B flange. What is the smallest value? Smallest one. So for T beams with flange on both sides of the web, the effective flange width is limited to the lesser of smallest value according to ACI section 6.3.2.1. 1/4 of the beam span, the web width plus 16 times the slab thickness, or 1/2 the clear distance of the adjacent web, center line to center line. This is the first case. If you are talking about intermediate beam, we have a slab on this side and a slab on the other side. Sometimes your beam is edge beam. Edge beam. That means we have only slab from one side. We don't have anything for the other side. So, in this case, we have another situation. T beams with a flange on one side of the web only. The effective flange width equal 1/12 of the beam span. Your span divide 12. the web width B web plus 6 times H flange, or 1/2 the clear distance from this center line to your beam. So what is the smallest value? So we have two situations. Sometimes here is your slab thickness, sometimes your beam at the edge, sometimes your beam is intermediate beam. We are talking about how much width of your slab is working with your beam. If your beam is intermediate, so we have something here, a little bit of your slab with effective width B flange, maybe quarter span, maybe 16 H plus B web, maybe center line to center line. Center line to center line means we have another beam here. So between this beam and this beam, we have a center line here. Between this beam and this beam, we have a center line here. So sometimes maybe your B flange is like this. Anyway, we have 3 values. Use the smallest value. If your beam is intermediate beam, but if your beam is edge beam, we can expect a slab from one side only. So your B effective can be, or your B flange, 1/12 of the beam span, L divided 12, or B web plus 6 H, I mean by H this value, H flange, or center line to center line. This beam has only one center line, so this distance can work. So we are trying first to determine what is your cross-section dimension. Anybody remember how can we get the total thickness, H? Yeah? If your beam is simply supported, your total H equal span divide 16. We have a table. Do you remember this table? No? Yeah.
Honestly, no. 10.
Do you remember this table?
No, I did. Yeah.
This table can tell you if your cross section is rectangular cross section, can tell you what is the total depth, H. If your cross section also is T section, what is the total depth? Based on what is the type of your beam, simply supported, or continuous from one side, or continuous from both sides, or cantilever. Today, I tell you, hey, your cross section today is T section. That's fine. Your width here, do you remember how much? 12 to 15 to 16 inch. That's fine. But today, I'm talking about T section. So we missed something. What is the dimension for your flange? We talked about this one just a few minutes later. So B flange may be span divide 4, 16 H flange plus B web, or center line to center line, which is the smallest value. So I can figure out what is the value of B flange. So right now, your concrete dimension is known. We would like to know what is the area steel, or we can assume area steel, and what is the design moment of resistance. Actually, we have two situations. First one is very simple. Second one is very not simple. First one, do you remember first step to solve rectangular section? Yeah, we have tension in one side and compression on the other side. That's right? In between, what do you have?
Neutral.
Perfect. Your neutral axis is here. Or your neutral axis is here. Or your neutral axis is here. Or your neutral axis is here. I don't care. You have a distance C. That's right? But I have problem here. Because sometimes your neutral axis is here. So this part only is under compression. And the remaining part under tension. Sometimes your neutral axis is here. Oh, it's a big difference. Because the first case, your neutral axis within your flange. The second case, your neutral axis within the web of the cross section. We have a big difference. But in your rectangular section, it doesn't matter. Here, like here, like here, like here. All of them rectangular. This part, rectangular part. This part, all of them the same shape. But here we have a big difference. Because if your neutral axis on the flange, this part under compression. If your neutral axis is here, wow, we have this part under compression. So we have different shapes. It's more complicated. Okay, so if the neutral axis falls in the flange, your neutral axis between tension and compression in your flange, then your calculation is very simple, like rectangular section. We have stress here, 0.85 F prime C. We have compressive force, C. We have another tensile force here, T, equal area steel, F yield. We have equilibrium. So your C